Hey, Ben Pearson, the Roaster Tracker, and today we're going to talk about a ability for science and engineering to see something that was previously thought unseeable, and that is a black hole, including its accretion disk and surrounding things. Now, what we're looking at here is in Universe Sandbox. I have a simulated black hole about the same size. It has kind of a ring around it that's similar to the accretion disk, and you can kind of see what it would look like. We'll zoom in a little bit just for fun, and you can see the gravitational distortion that happens here. But as we zoom out, and let's take the field of view, make it tiny, you can see that the gravitational lensing is kind of less of an effect when you're this far away. But it's still a pretty neat effect, and this really looks kind of similar to what it looked like when we saw the pictures. An effort for the Event Horizon telescope to combine several of the most powerful radio telescopes that are in existence together into the Very Long Baseline Array. And by so doing, they were able to use a technique called interferometry to image something that is this far away. This thing is tiny. Everything you see here is maybe the size of an orange, or maybe even smaller, that is on the surface of the moon. So this is some massively, very, very detailed simulation. And to do this, they needed to have a telescope the size of Earth. So what we're going to talk about today is a little bit about how they managed to accomplish this great task. I have a website here that I've created, and never mind the fact that it says it's part of Where is Roadster, I just use that as a kind of backdrop for it. And this kind of helps us to understand what interferometry is. Now, interferometry is the ability to combine any kind of light from two or more sources together into some kind of a single image here. And so what I have here, the bottom here is a diagram of what this actually looks like. So we have some light source here that has some waves that are coming out, and it goes through a couple of slits. You can barely see them, but here they are. And when it goes through those slits, they have some waves that will act. So we're going to go just kind of increase the distance here. You can just see some notational waves here. And this is kind of like how the Very Long Baseline interferometry system works. They have a number of telescopes that are throughout the world, and they act together as one single body combined together to be able to get a much higher resolution than they would be otherwise. And by showing how this works, this is called the two-slit example, it will show us a little bit about how the much more complex system works here. So I just want to show a couple of things. First of all, let's go and show when the two slits are very, very close. This is, well, right now they're actually on top of each other. So this is how bright the light source is, that you just have a single dot here going through a scene. And it's kind of uniform. You don't have any particular resolution. This will all kind of just show up together. If I move the location of the source a little bit, you actually don't see any difference in the raw output signal, only in the brightness, if you look here at the scale. So let's go ahead and put this back in the center at 50. 50, there we go. Close enough. Now let's go ahead and give it a little bit broader here. Now what we're going to do is move the same source around a little bit, and you can see that the waves shift. By having these two slits that are the two kind of observing states, there's a shift whenever you move the target around. Now there's kind of a limit, something like this looks a lot like something like this. So you have to be focused on a much narrower part of the sky. But assuming that you can do all of that, then it works really well. So if we go and do something that's a very wide baseline, then you can see we move around just a little bit and it will make all the difference in the world. You can kind of get some sense here. Now this isn't exactly how the long-range baseline interferometry works, the VLBI, but it kind of works as an example. Essentially, by making a virtual telescope, by recording the raw radio waves that come from here and simulating what would happen if they bounced from that point to some kind of a telescope that was at some far distance that was the size of the Earth, then you can get a really good sense of how things look at a very distant spot. Now, what are the problems with this? Well, the biggest problem is that you have just these tiny dots here to observe things, even though there's this whole huge distance between these two. And because you only have these two tiny dots, the amount of light that you receive is less, and B, you don't get a complete view of the picture. See, in this video here, from the EHT team, you can see here a number of telescopes combined together. And by having these pairs of telescopes that are at very far distances, they essentially get 2 points of data. They get an image that comes from the telescope at one point and at each of the two baselines. By having 3 sets together, they can actually cancel out some of the errors and it'll be even smoother acting. But they really need to get a very complete picture to have everything working perfectly. And the way to do that is by having the Earth rotate. So as the Earth rotates, then you continue to take this picture over a long period of time, then you effectively have a much larger space. And you can see all of the dots start to fill out, and you start to have something that looks reasonable. So they essentially have an image that's at each one of those points along the telescope. You can imagine if you have 1,000 pixel image, then maybe you have 100 pixels worth of data, or maybe even 1,000, but you're still missing a significant portion of the data. So how do you combine all of this together? And this data is immense. They said that there's about 1 ton of hard drives that was used to contain all of the data for this experiment. They actually found it was faster, even though they have high-speed systems at some of these sites, it was faster to take all of the data, write it to hard drives, and take it by airplane to the site where they could collect all of this together and do all of this processing. And it took them a year to do all of the processing to come up with the image of the black hole. How did they take this massive amount of data and produce the image that we see? Well, they first started by bringing it all into one spot, as I mentioned, and then they started to filter this out. Now, we had 5 terabytes worth of data, which is an enormous amount. They needed to figure out what of this data had the same signal, the same wave, so that way they could actually compare them together. And so they did some filtering on this to try to do things. They basically matched the signal in time and looked to see if they seemed reasonably good match. They could check to see if the same frequency was being used and overall get something reasonable. So that took the data down from about 5 petabytes of data to about 5 terabytes of data, which is a size that is a lot easier for me to imagine, at least. But they still had a lot of work to do. And then the next step was something that took a lot of handwork, and that was to figure out what of this actual data could be used. See, there's a lot of errors that can creep up in doing this kind of process. Anything from atmospheric effects to slight variation in the Earth. The Earth will expand and contract every night, and so it will have some issues there. And overall, they just need to figure all of these details out so you can get the purest data to the image correlator so you can produce something that actually is meaningful. This is where probably the most amount of work is done to reducing the data, probably some of the most important work. And that takes the data down to 1 part in 10,000. So you're going from about 5 terabytes of data to about 100 megabytes of data. Much more reasonable. But you still don't have an image from that. So you have to correlate all of these images together into something that will look like a final product. Now, what they'll do is something kind of similar to the 2-slit experiment that I was showing earlier. They will run through a backward simulation of there. They basically project what would happen if the wave bounced off of a telescope and combined together at the appropriate distance. And with this correct focal length, then they can basically make an image that we can actually see something meaningful. Now, they don't have a complete picture. As we saw earlier, there's a reasonable amount of the Earth that's covered due to the rotation of the Earth, but there's still a lot of gaps in there. And so that's why the final image looks very fuzzy. You can imagine that there's a few pixels, like you can see here of this picture of Earth, with the telescopes moving across it, but you have to understand where that comes from. Now, the reason they're able to do this is images actually don't show up as a perfect point. They have a kind of spread to them. And so you can run these images through what's called a deconvolution kernel, where you're trying to combine them together and predict at a higher resolution what the image will look like. And there's a lot of different image algorithms to do this. They sent the data off to a number of different teams, and they all produced an image that looked reasonably close. You can see the three images that three of the teams produced. There were about 10 total teams, and at least 4 of them showed essentially the same thing. And they combined them into a little bit more detailed combined image, and that was the final product that we see here today and that they presented at their press conference. But it's pretty neat that they were able to do this, and it fits so well with Einstein. And the same kind of algorithms were used in a number of different places. You can see here in the Chirp Algorithm paper what some of the data sources look like before and after. Now, the Chirp algorithm was a result of a research paper by Bouman, who was one of the leaders of the teams that produced this image. But it's not the only team that did it, and it was a very useful one. You can see just how much of an improvement that this algorithm was versus what had been there previously. But this is one of many algorithms that was chosen. And so, and the end result is that this looks pretty neat, and we were able to successfully image a black hole. I can't wait until they do something else with this. Maybe they'll try imaging the black hole at the center of our galaxy. It's a little bit difficult to do that now, as I understand, but within a few years, the stars will move far enough where it'll probably be okay. But thank you guys so much for joining me. Let me know whatever questions or comments you guys have. And until next time, keep on tracking. Take care.